Okay, so today we start the topic of inference. Okay? Inference is the whole rest of this semester. Inference is a something that has really changed the world in terms of production and producing items. So I want to give you one real life example to kind of give you an idea of what's going on there. Why is that? How many of these are on? Okay, there's like 3 of them. So let's do some. Take some on. All right. If you think about, say, the 70s and in the 70s and 80s, 1970s and 1980s, let's talk about car manufacturing. Okay, back in the 70s and 80s, foreign cars really led the industry in their quality, in their reliability, and in their lower costs. Okay, so we're talking Hondas, Toyotas, what was at the time Datsun, but now it's Nissan. So anyway, so that industry in foreign markets and the Asian markets was very much more superior to the reliability and the functionality of American-made cars. All right, and the reason for that is because the foreign markets, the people that led that production, trusted statistics. They understood that they could take a sample, and then from that sample, predict or conclude or estimate whatever they were wanting to do for the whole population of their assembly line, their car that they were making. And so because of that, they only had to take one sample. They saved a lot of time. They saved a lot of money. And so with that extra time and money, guess what they could do? Put it into improving their product with what they found out. Well, so over here in the American market that did not rely on statistics, we were still collecting data and understanding our vehicles in a very cumbersome and inefficient method, so that we did not have, we were using our time and money inefficiently. And so we did not have all that extra time to do that. Now, I think since the 90s, Americans finally caught on, started doing that, and so then that has now improved that marketplace. But that's one case where statistics really had a broad impact on those production models. Okay, so we're going to start this idea of inference. We're going to start this idea of knowing, taking just a sample, and then from that sample, inferring to the entire population, and then having some confidence in that. All right, so there are 2 kinds of inference. The first one, and the one that we're going to do today, is this thing called confidence intervals. This is where you want to know a particular thing about a population. Say, if I wanted to know the percent of my students that are like not doing anything, then I would take a sample. I have to make sure it met all the conditions, still conditions, and then from that I could infer or get an estimate. Okay. Here, what if I wanted to know the average length of a rattlesnake? I would get a sample of rattlesnakes, I would measure them, I'd get the average length of that sample. Now, question, if I just take that one sample, then am I going to be able to go to the encyclopedia or wherever it is and say, hey, guess what? I got this sample result, so therefore the average of all rattlesnakes is this. I'm not going to be able to do that definitively with my one sample that I took. No. Okay? Your sample is a ballpark idea. Your sample results get somewhere in the realm of the real answer, but it's not necessarily the answer because of sampling variability, yada, yada, yada. So we will then make an interval, which will give us an estimate. Hypothesis testing will come to starting next chapter, and that's a big old huge thing where somebody makes a claim, we collect data and see if we have evidence to reject or fail to reject that claim. So we'll talk about that later. But anyway, so we are dealing with confidence intervals. where we don't really know the population characteristics and we wish we did. So we create an interval of plausible values. We have a low bound and a high bound. So we're going to have a lower number. We're going to have two numbers, and we would expect the real answer to be located in that interval. Okay, that's where we're going. All right, so we hope that that interval captures the true population parameter. So at least we get that ballpark idea. Now, there are conditions you are going to have to get real over and over and over, and I'm just not even going to go into that right now because I don't want to get caught up in these details and miss the point. But because we will be doing proportions for the next 4 chapters, you will hopefully be able to solidify that the proportion large enough is that your NP and your NQ are both greater than or equal to 10. Okay? All right. And then, of course, upon all of our conditions being good to go or reasonable, something that sounds like it could reasonably be the case, what is our conclusion that we have to come to? Okay, good. That our normal model applies. Okay? So our confidence interval is based on the data, the sampling distribution falling into the normal model distribution. Okay, now let's actually take a look at the formula. This formula is on the back of your formula charts at the very top, and I'll show you that later. But it looks exactly like this. It is stated just like this. So you would turn over there, and this is what you would get. Now let's talk about what each of these items are. This statistic is what you collect, and that value that comes from the data you collect, the sample you collect. Statistic comes from a sample. So, depending on what kind of data it is, it's going to be either a sample proportion or a sample mean. You're going to be getting one of those two things. All right? And of course, this unit we're going to be dealing with proportion values. And then you're going to add or subtract. You're going to add to get the upper bound and subtract to get the lower bound. This critical value, and I'm going to talk to you about that later, so hold that thought. But you do know how to get this standard deviation of the statistic. This standard deviation of a proportion sampling distribution is, and you didn't have to have it memorized because it was on your formula chart, but anybody has it? What is it? Okay. All right. So we are familiar with that stuff there. Okay. So come on up here to the next page. I want you to rewrite that there because I want to reference this. Okay. I know you laugh, but inside I'm like, okay, that's okay. Okay, so when we have done problems in the past, for example, if I tell you 24% of the M&Ms are groovy M&Ms, and then you take a sample and you get 14% in your sample, then is that unusual? Okay. Well, what value, if I tell you 24% are the M&Ms that are created and I get a sample of 14%, what of those two values goes in to this P here for the standard deviation? The 24%, the true claim of the entire population. So you know we always want to put the true population P right there. Okay. But let's say that today we're going to do an activity where we are going to estimate the proportion of water on this globe. Okay? So we're going to estimate the proportion of water on this globe. Okay, so now I need to get the standard deviation of it, of this thing. So what should I plug in there for P? Okay, no, I don't care. Whatever. It's a proportion. It doesn't matter. It's a proportion, so you pick your units. I don't care. Okay, so what's our P? What are we going to put in there for P? Ah. Yeah, the real answer. Well, what is the real answer? Oh, no, guess what? No, 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 no. We don't know the real answer because this is not necessarily anatomically correct. Now, hold on. I know it was a trick question. It was a trick question, so hold your thought. Hey, this globe came from the Oriental Trading Company, and, who knows, it cost half a cent to create. So I am sure that this is not a perfect replication of the Earth's water and land proportion. So we don't know what's on this globe. Guess what? We do. We have to guess because we're going to be inferring. So we do not have this. So we do not have this true population P to put into this formula because that's what we're trying to estimate. So yeah, we don't have it. Okay. So what do? Okay, we're not exactly guessing. What are we going to use? So we will settle for, we are going to collect some data. And so it's not really a guess. It's going to be like an approximation according to our sample. Yes, it's going to be an approximation based off the sample that we collect. So what is that? What's the, how do I notate that? P hat. The samples. We will have to settle for P hat since we don't have the real P. Okay, good. So, in summary, always use the real P if you have it. Okay? But if you don't, then you will settle for the P hat, okay? Let's talk about the P hat section. My grandmother actually used to have a pecan, but okay, sorry. We are going to skip. I'm sorry when I just started about that. I know, I just started thinking about that. Okay. All right. We're just going to leave that there and just forget it. Okay. But see, the problem is that from now on, whenever I say that, that's what I'm going to be thinking about. But anyway, it is called P hat. That's our little thing. Okay, we're going to actually skip. We're skipping the rest of this page because this kind of gets too deep into some theory stuff, and we're going to come back to that after we know how to compute. So let's go to our activity. So here's how the activity works. I want everybody to take a pen, and I guess you could use a pencil, but I don't think it would work very well on your finger. You need to put a pen dot on your index finger where you would be catching this globe. Now here's why you do this. Because in a minute, I'm going to put you in groups of 3. And you are going to have 2 people toss the globe back and forth, and 1 person will record the data. So for example, if Zach tosses, he just wants to spin it maybe so that it's randomized, so send it to me. Let's go. Oh, I missed. Okay. So here it was. Of course, that's pretty random. I got it. Now, see, if I didn't make a dot on my finger is on both land and water. Okay. So see, then what would you call that? So the dot is a small enough. Yeah, there would be bias in there. Absolutely. So the dot's small enough that it's going to be on land or water. So I'm going to look, and if it's on an island, then you put land. If it's on a sea or a lake that's big enough to show on the globe, or a canal, whatever, you put water. So mine's actually on water. So that would be what the tally person would record. So you are going to have your tally person record 50 tosses. So everybody's going to have the same. What? Oh yeah, I got more. Yes. So you will do 50 tosses. So we will all collect 50 pieces of data, and then we're going to go from there. Okay. So now that you guys have your data, we're all going to get a little bit different confidence interval because you all had a different sample. So, but let's first talk about what your sample is representing. representative of. Just hold it. So what does every single one of these p hats mean? Represent. Probably every time you start with a p hat, you would start with proportion because it's a proportion amount. So it's the proportion of what? Yeah, what sample? Because every single one of them that makes up a sampling distribution has to be the same size. So ours were 50. The proportion of 50 tosses that landed, no pun intended, on water. Okay? So the proportion of 50 tosses that landed on water. Now you are going to put your p-hat data next. Yours is going to be different from mine. My group had 30 out of 50, which is 60%, so I'm going with that. So write yours down. Okay, now, after you get that down, write the formula. This we won't have to do it all the time, but we do this first to baby step you through all the values. So write this down. The confidence interval is your statistic plus and minus. So, I mean, we're doing words right now. Your critical value times the standard deviation of the statistic. Okay, so now we're going to actually start putting these numbers and learning how to finalize and actually compute this confidence interval. So, your statistic is what you put here. My p-hat, and we're computing here, so I'm going to do it in terms of a decimal, was 0.60. Okay, you put your p-hat there. Your statistic. And then we got plus and minus. And still hold that thought on critical value. We'll come to that in a second, but let's do this standard deviation of the statistic. Let's go over to the side and compute that. You know that it's going to be the square root of p times 1 minus p over n, but you don't have p, so you are going to have to settle for p-hat. So in my case, mine's the 60 and the 40, so you do yours. Your numbers are different than mine, but our n for everybody is 50. Okay, so do that number real quick. Okay. All right, so everybody has their own standard deviation of a statistic. Okay, so now let's learn what this critical value is. If you turn to the page behind you, this is where we're going to learn critical value. Okay. A critical value tells us how many standard deviations we are away from this data we collected. How many standard deviations are going to go out? So what do you know that we've done already that is this idea of the number of standard deviations? Yeah, that's similar to the z-scores. Take it back. So, sorry. But, so the z-score is going to be our number of standard deviations out, okay? So this critical value is going to kind of be built off of the z-score. And the z-score that you are going to use is going to be determined by how confident you are told to be in your interval. So it will tell you in the problem, I want you to be 90% confident, or 95% confident, or 99% confident. Those are common confidence levels. All right. So let's actually construct a few of those now. In a minute, I'm going to have us all be 95% confident on our globe estimate, our water estimate. But let's do this. Let's start. can't really see necessarily everything over here on the side, so I'm going to practice constructing this with you. A 90% confidence critical value. Okay, so here we go. A critical value comes from the confidence level, and that's what is in the middle of our normal curve. So if they want to be 90% confident, then you have 90% in the middle, which then gives us two tails. So if you have 90% in the middle, then how much is in each tail? 5%. Okay? Now, how can I get this C-score right here? That's going to be the critical value. How do I get that? Inverse norm. Inverse norm of one tail. That's what should go through your mind every time you want critical value. Inverse norm of one tail. Inverse norm of one tail. And if I go put that in my calculator, I get negative 1.645. And I want you to go to 3 decimals. The 95% actually rounds to 2, but here we go, 3 decimals. So look here. If that lower one is negative 1.645, then what's this other one? Positive 1.645. So guess what? On the formula, by the way, and you don't have to turn over yet, so I'm not putting in numbers yet, that is where this plus comes from for the positive critical value, and this minus comes from for the negative critical value. So that plus minus is what is representing this lower critical value and this upper critical value. Okay? All right, so now let's do the one that we're going to use, which is 95% confidence, okay? So let's see if you can't do that one. 95% confidence, critical value. Because of the way the decimals are falling, you have to round to 1.96, so that puts this one at positive 1.96. So our critical value for 95% confidence is 1.96. Now, before we go over to the other one and finish our interval, I want you to do one more on your own. Everybody right now, figure out your 80% confidence critical value. In the future, you do not have to draw these pictures every time. This is only the concrete for today. We're doing it concretely, so you get what's going on. Okay, see if you got that. Okay, so in the future, we should start getting to the point where you are visualizing this without having to write it down. You're thinking, okay, that confidence is in the middle, so you can tell what's in each tail, inverse norm of one tail to get that critical value. So let's go over here and compute our interval with 95% confidence. So I'm going to put 1.96 here. Put your 1.96 there. All right, now, this piece here, this critical value times the standard deviation of your statistics is what is considered the margin of error. That's that leeway that you have above your statistic and below your statistic. So this is technically called the margin of error. All right, so I'm going to compute what my margin of error is. Go compute what your margin of error is. Yeah, just multiplying those two. Okay, so now that you are to this point we are about to finish up our interval. Our interval will be notated as it looks like an ordered pair, but it's actually not, okay? So, put your little parentheses like an ordered pair. So what happens is we put the upper bound, of course, on the right, and the lower bound on the left. So how do I get the upper bound? I use the addition part, the p hat plus your margin of error, and that will give you the upper bound. So do yours. Do your p hat plus the margin of error to get the upper bound. So then how do you get the lower bound? Point subtract your margin p hat minus your margin of error. Okay. So on AP tests and all multiple choice stuff, they will probably be presented to you in decimal form. However, I'm going to have you write these as percentages so that, as we go through this course and you're thinking of things in context, it just makes more sense that way. So go ahead and write our confidence intervals in percentages because you can always then translate it to the decimal when needed. So this is 46.4%, just 3 significant digits is fine, and 73.6%. So that is the range. I am saying that I'm 95% confident that the true proportion of the water that's on this globe is somewhere between 46.4% and 73.6%. Okay? Y'all's is good. I want to talk about that later. Okay? All right. So, you may not be, if I was a scientist, do you think I would be happy with this variation of an estimate? Yeah, no way. So we need to talk about how can we make this more or less varied? How can we make this less varied? Okay, so let's consider these questions here. What's going to happen if you throw the globe, and instead of putting 30 to 40 more times? What's going to happen if you throw the globe 30 to 40? Well, hold on. What of our variables changes? 30 to 40 more times, increasing our sample size. What variable's that? Okay, n. N, your sample size increases. So people, look up here. Boom. This 50, if it's changing to 80 or 90, then what's happening to the value here? It is getting smaller. So our standard deviation is getting smaller. And if our standard deviation is getting smaller, this number is getting smaller. So this product that makes up the margin of error is getting smaller. So if this margin of error is getting smaller, what's happening to the size of my interval? It's getting smaller. It is getting more closely clustered around the p hat. Have we heard that before? A smaller standard deviation is shrinking this interval in. Let's finish these questions out. So n is increasing, which meant that the standard deviation is smaller. Okay, and then the next one says, so how will that change your confidence interval? And so it then gets what? Smaller, less varied, more closely clustered around the statistic, or p hat in this case. Okay, so now here's a phrase that we're going to start using, and we're going to start using it anytime we have context, which your homework doesn't. But what we say about our confidence interval is we say this: I am 95% confident that the true proportion of water on my globe
introduction, one quick announcement for our last photo group. We need, when the bell rings for passing period, we need the Young Republican group to meet in the journalism room.
Between your two numbers. Mine is, now hold on because there's a typo on the lesson I got to tell you. 46.4% for me and 73.6% for the upper bound. Now, we've got a few minutes. I have to tell you about the typo on your homework real quick. Okay, so here we go. All right, I'm gonna do number one with you if we have time, but I don't really know. I think we're running out. But look here. This is problem number 2. I did a lot of copying and pasting, and you need to fix this. Anytime it says 98% confidence here, this should be 98% confidence critical value that you're finding there. I boo-booed when I copied and pasted. I didn't change that. So if here it says 96%, then this is supposed to say find the critical value for 96%, and so on. Okay? So this one's 80% here, and 94% here. Okay, so let's go ahead and do this number 1 together. Okay, so when I read this problem, I'm going to fill out the variables that I read it to be. So we start off when we say we have a sample of 100. So I know my n is 100. And the probability of success is 0.73. So that means that my p hat is 0.73. And I want to construct a 90% confidence interval for the true proportion. Okay, so first on all these, I'm going to have you identify the critical value for this percentage that you're going to be dealing with, so 90%. Now, we have done that before. We know that it's inverse norm of 1 tail. And if 90% is in the middle, then 5% is in each tail. So inverse norm of 1 tail gives me negative 1.645. So I'm going to be dealing with that critical value. Now, for the work, you do not have to write the entire formula out from the beginning in words. You can just go ahead and start plugging it in. So the first thing you plug in is the statistic, which is our p hat. So that's the 0.73 plus or minus the critical value. Well, I have the signs accounted for here, so I just put the 1.645. And then I'm going to multiply that by the standard deviation of the statistic. So how do I get that number? Well, you're going to have to come over here to the side and figure out the standard deviation of that sampling distribution is the square root of p times 1 minus p over n. But you cannot, you don't have a real p, so you are settling for p hat, which is your 0.73, 0.27 over our sample size of 100. That number, when you compute it, is 0.0444. And then you will go through here and finish these two things here and go ahead and write them in percent, because we're going to end up using that to understand context anyway. All right, so that's what I want you to include on those. Just make sure that you have fixed this little typo here that that I had not finished corrected on the copy and paste. All right, so that's it.